Hey everyone, Mr. Hausman here. We're going to take a look at our first lesson on electric fields. It's an extension of our understanding of charges and allows us to connect electricity, magnetism, and even some past topics like gravity. So when the first time you hear about a field in physics, it sounds like it's made up. It sounds like it's just a convenient way of explaining something. But really, when forces act at a distance, the best explanation is through a model called fields. And a vector field, or any field in physics, we're on page number 2 here, is a quantity whose value depends on the distance relative from a source. So every field has a source. The field also has a vector characteristic. And so we know about vectors. We know that they have magnitudes and they have directions. So a field can be described as having a magnitude and a direction to that field. So we're going to be using some vectors again, but I'll give you a hint. The vector addition here is going to be very different and in some ways much more challenging, so we will let software take care of some of the vector addition for us. So let's kind of figure out what the heck is going on with a field. Let's think about heat. Let's think about a campfire, or maybe a fireplace or a wood stove. So when you have a source of flame or heat, right, maybe in the center, and everyone in your family is around the fire pit and enjoying themselves at a campfire or whatever, you notice that if you stand a certain distance away from the fire, you get the right amount of heat transfer. Maybe you like it very close to the fire, maybe you like it a little bit farther back, maybe you go back and forth. But the distance from the fire has a big effect in how you feel that heat transfer. So if you put your hand at a different distance from the center, your hand is going to feel a different amount of thermal transfer or thermal energy. So we have thermal or radiant energy that's being emitted from the source. And this is a little different. This is not truly a field. But when you have a flame and there's some combustion going on, right, the closer you are to the center, the more thermal energy you're going to feel per square inch of your body. Right? So if you stand facing it with your body versus your shoulder, that's different surface area. And but the closer you are, the more energy per square inch you're going to feel. The source of the field is, of course, whatever's burning. Maybe it's wood, maybe it's coal, or maybe it's one of those gas fireplaces, that are out on patios these days. So there has to be a source. And there also, in order for it to be considered a field, there has to be no contact, direct contact between the source and the recipient or the thing that's detecting the source. So in this case, it's your hand or your body. So a major difference is there has to be a source and there has to be no contact. And if you're making a connection to induction, that's great, but not really needed here. Thermal energy transfer is a little bit like a vector field in that it spreads out in all directions, and how far away determines how strongly you feel that heat. So let's go to a field that you actually know a ton about already, gravity. Now this fall, a couple of times I tried to introduce, just really subtly, that every time we talked about gravity's acceleration, 9.8 meters per second squared, I kind of hinted that there was more to that number. Let's actually write that number down because we'll be using that, 9.8 meters per second squared. And we, of course, know that that's the acceleration. And we called it negative because it was inward or downward toward the planet. But I'm here to share that gravitational acceleration is also the same exact magnitude of Earth's gravitational field. Okay, so Earth's gravitational field is a G field. That's what we refer to it as, a G field. It's a vector field, but we call it G for gravity. Okay, the strength of gravity is the same along each of those circles. See in this picture that looks like a bullseye, Earth, and let's make it blue because Earth is the blue marble, okay, with lots of oceans and things like that. No matter where you are at a distance from Earth, you're going to feel the same gravity. Now, we always referred to the 9.8 as if you're on the surface of the Earth. But if you are some distance away or even further out, gravity actually changes or decreases with distance. The further away you get, the weaker the gravitational field, or the attraction felt by G. Okay? So any mass put anywhere in that field will experience an attraction force, right? An attraction, a pulling force toward the center of the Earth. The closer you are, the stronger the pull. Let's kind of examine that. So this gravitational field has a name. We call it gravity. It's got a source, the large mass. So every single field has to have a source. It has to have a direction. Well, the gravitational field of our planet is an attraction, so it's inward toward the core. And you can see that there's little arrows located on radial lines, but they all point inward. So how do you describe it? How do you describe its magnitude? It's inward in direction, but its magnitude is G. And the unit for G is now going to be used as 9.8 newtons per kilogram. And that's, we use that in another sense this fall, but that says that if you're a 1 kilogram mass and you are in Earth's gravitational field, you will feel a pull of 9.8 newtons. If you're 2 kilograms, that'll be twice as much force. 3 times the kilograms, 3 times the force. So the more mass you have, the greater the pull. The source, again, was the planet's mass, but anytime you put another mass, a rock, a human body, an airplane, right, they all get pulled inward toward Earth. So here's something new today, the electric field. So the E field, or the electric field, is created by a source that we refer to as Q, and it's the source charge. And that E field that is created by every source charge is continuous in every direction. It spreads out indefinitely. It goes on forever and ever, to infinity, not and beyond, to paraphrase the old Buzz Lightyear. But it's an infinite distance in every direction. So the field exists at every point in space, R, right, around the sphere. So if here's our source charge Q, this is a little weird, but let's explore this, and you measure out distances R and R. And B and C look to be about the same distance away, and I think they are if you measured it with a ruler. And positions A through F have different E field strengths because they have different distances from Q. Well, C and B look actually very similar, and I don't know if you can tell this, but A and D are actually about the same distance away too. So maybe it's not every single position has a different field strength, but really has a different, there's several that are similar to each other. I'd say F and E are all out there by themselves, right? F is a certain distance away, and E is clearly the farthest. So the farther away you go, the weaker the field gets, okay? So how do we characterize an E field? Well, let's call it by its name. It's called an electric field, or E field. The source is a charge, and we refer to it as a source charge, but it's also considered to be tiny. If it's a large object like a Van de Graaff generator, we will still consider it a point in space, even though it does have some physical dimensions. Now, in this case, we will find out that E fields can cause attractions or repulsions, just like the electric force can. So the field can have a different effect on what you put in that field. So how do you describe it? Well, an E field is a magnitude, right, that has a certain amount of newtons, because it's about the forces that are felt on objects in that field, divided by, not by kilogram, but by how much charge they have. So if you have zero charge or neutral charge, then the E field has no effect on you. And so fields create forces. That's one of the big take-home messages for today. So let's do a little more detail. The electric field surrounding a source charge has a specific magnitude, right? So you have to have a known magnitude source, okay? The charge source alters the space around that object. So having a charge in space changes the region around it, the space around it, in a way that all other charged objects can feel a force without any contact. The large source can attract or repel. That's a pretty key idea we've already mentioned. But other charges, but in its field, depending on the amount. Oops, sorry, I meant to put in the correct word, sign. So it depends on whether it is a positive or negative charge that you're dropping in. And an E field is a region in which each point in space, right, is... Sorry, let me go check this. This is one that's kind of been actually twisted me twice today. I'm so sorry. Yeah. This is the big idea. Can't believe I had to check that. It's a space where each point in space is experiencing a force. Now, you have to meet the criteria to meet that force. If you have a charge, then you will respond to an E field. If you have a mass, you will respond to a gravitational field. And there's a few others that we'll talk about. So the direction of an E field tells a little bit of a story. So when your source charge is positive, so this huge positive, even though we talked about it being a point source, right? E fields always point away from positives. And I'm not drawing them perfectly spaced, but those field lines, these are vectors that show the field, right? They always radiate outward, and we'll talk about how to draw those, okay? So in it versus if you have a negative source, they point inward. And I am trying to spread out my field lines pretty evenly. So the question is, what happens if you put a test charge, which is a small secondary charge, not the source, that is dropped into that E field. And we know that charges near other charges experience force, but now we're explaining why they experience a force. So if you have a positive source and you drop in a positive test charge, just to kind of check out what happens, isn't the direction of the field and the force always outward, right? Don't positives and positives repel each other? But if you drop in a negative test charge, the charge, which of course we might call an electron, is going to be attracted inward. Likewise, a positive test charge dropped into a negative sphere would get drawn inward, and a negative dropped into a negative source charge would be repelled. And that's kind of just restating what you already know about charges, what like charges repel and opposites attract. But now we're kind of explaining it from the concept of a source and a test charge. Okay, so how to draw electric field lines or electric fields. Let's kind of zoom in on this. So here are the two most basic field line diagrams. So this is a field line diagram for two electric charges. So we have a positive and we have a negative source. These are sources, not test charges. So the field lines that you draw in show the direction of force that a tiny positive test charge would experience. So it's easy to remember that they always go in the direction of what a positive test charge would do. In fact, that's what a test charge is often referred to. It's like a single proton. So look at these vector arrows. They are all pointing outward on the positive. They are pointing inward on the negative. And you ask yourself, yeah, that makes sense. What would a positive experience if it was dropped into the region around a negative, and it would be drawn inward? And so that's how we draw the field lines. They come out of positive and in toward negative. Okay, so let's say that again. Vectors point out of a positive source and in toward a negative source. The line density, so when you're drawing these lines now, think of this now as a drawing. And the density or the closeness of the lines determines or shows the relative strength. So the closer the lines are together, that means the stronger the field strength. So these E field lines are kind of shown evenly spaced out. But you notice that at a short, close distance away, they're pretty close together. See how the neighboring line is not very far away. And that tells you that the E field is strongest closest to the source. How far away are these lines out here? Well, that's clearly a greater distance. They're more spread out. That's how it works with like a starburst or like a ray pattern like that comes out. So the picture shows that the field is strongest when the lines are closest together. Okay? E field lines never cross. Okay? The vectors can bend and affect each other, but they will never cross. So there will never be a time when in a complex diagram you have maybe multiple source charges. The field lines will always do vector addition, they will combine, but they will never cross each other. I'm so sorry, we're going to check number 5. I don't know why I left them over here. Okay, we're going to skip 5. Let's keep going. Okay, so what if you have multiple charges near each other? What if you have a charge that's negative and positive, and they are kind of equal distance from a center point, and you're trying to describe, well, how strong is the field and what direction is it going at different positions? And what you would have to do is you would have to add vectors. So for example, this negative charge, right, if it was by itself, would have arrows pointing inward, and this positive would have arrows pointing outward. But do you see what happens? The tail of this vector and the head of this vector are crossing. So instead of crossing, they tend to bend or connect. So in this case, they would bend together. And let's examine that in more detail already drawn. So when two vectors, right, one's pointing outward and one's pointing inward, and you try to smoothly connect those, what you get is almost the pattern that you might expect to see for a bar magnet. I don't know if you're familiar with this for the magnetic field lines of a bar magnet, but when there's a north and south end, the field lines connect from one end to the other. However, if there are two like charges near each other, these are both sources, source 1 and source 2, and their vector lines are trying to both radiate outward, especially in the middle region, and they can't cross, but if you add them together, you're going to get a smoothing out effect. Likewise for this drawing, but these are two negatives. Now look at the comparison of the two positives and the two negatives. It looks like the negatives are just like super heavy duty enforced, but what you know about this is that this source must be much more negative than these guys.